Well, hello everyone. Thank you very much for tuning in for this afternoon session, and apologies for the slight delay, but I can assure you it's certainly going to be worth it. My name is Christopher Martin. I'm Treasurer of the UK Urban Design Group. It's a pleasure to welcome you to the Urban Design Summit at COP26 in Glasgow from the Urban Design Group. As well as my role at the Urban Design Group, I'm also a trustee of Living Streets and co-founder and director of Urban Strategy at Urban Movement, an urban design practice that was founded to investigate the moments in cities where everyday life meets transportation. We're coming to you live from Glasgow, and up now we have our main keynote session of the summit, and we have assembled a breathtaking array of international expertise around this virtual and physical room, who will set out how we need to design settlements for changing climates, as well as how we can set in motion genuine climate repair. First, and joining us from the studio here, we have Dr. Shaun Fitzgerald from the Centre for Climate Repair at the University of Cambridge. Shaun will be speaking about the barriers to a deep and rapid greenhouse gas emissions reduction globally, nationally and locally. We'll then hear from Dr. Christina Hill from the University of California, Berkeley, who will be setting out how we need to rethink urban landscapes to adapt to rising sea levels. And a special mention to Christina for joining us from about 4:30 in the morning where she is. So thanks very much for that. After that, we'll have Professor Zongbo Shi from the University of Birmingham here in the UK, and he'll be speaking about how we need to rethink urban design to protect us from negative air quality. And closing the keynotes, we'll hear from Dr. Maya Negev from the University of Haifa, Israel, who'll be speaking about how we need to design to protect from increasing heats. So we're going to be hearing from our speakers making their points for around 25 minutes, and then we'll have time for all the questions we want. We'll pause for questions after the first speaker, as Shaun needs to head into COP itself. So please do get your questions for these formidable experts in the chat from the get-go, please. So without any more waffle from me, Shaun, would you care to tell us about climate repair?
I will. Thank you ever so much indeed for that lovely introduction, Christopher, and lovely to see everybody else as well. So I'm going to just use some slides to aid the discussion this afternoon. So I'm just going to share my screen, if that's okay, or try and do so, please. Great. So Chris has asked me to think about and speak about some of the barriers to tackling climate change, and in particular the barriers to perhaps the role that we should all have in our minds as we are looking at the built environment, on how we go on in these 2 weeks of COP, look at deep and rapid emissions reduction. So I just wanted to put in context, first of all, what basically the forecasts look like for carbon dioxide emissions. Look, the business as usual scenario that we've seen here, this is a projection from actually from BP, the Energy Outlook in 2020, which is basically a plateau. I even find that perhaps just a bit too optimistic, given some of my recent readings of various activities, when we hear about certain fossil fuel companies actually projecting, even in the next 10 years, to still see rather increased use of fossil fuels. But where we need to get to is a long way apart from that. We need to get to basically close to zero, if not zero, in a net basis by 2050 on a global basis. That's what we need to do, and it's the business as usual scenario is what scares me, because we need to think about what we can do to go and bring ourselves to either a rapid transition or a net zero transition by 2050. It's quite helpful to look at the energy consumption by end use sector, and the pink bit at the bottom there is indeed the responsibility of buildings, and we represent a decent percentage of this. The chart on the right is something that really does concern me, because under the business as usual scenario, what it's showing is the fastest rate of growth of use of energy we're responsible for. That's what the buildings, that pink bit on the very far right, is the biggest chunk in terms of percentage growth. So we've got to do something about it. And it's one of the sort of ways to sort of look as to what we can do. This is where are the big culprits. So this is looking at the difference between an air-conditioned suite of buildings and naturally ventilated buildings. There's, broadly speaking, a factor of 2 difference in the energy consumption. And what you'll see on this chart is that the one on the right-hand side is the mechanically ventilated air-conditioned building. the lion's share of the difference between an air-conditioned building and a naturally ventilated building is ascribed to the use of fans to go and blow air distributed within the space, bringing air in, blowing air out. Interestingly, you can still make some differences by moving towards a more naturally ventilated building, for example, in reductions in the lighting load, that's the green on the chart. Now, it's not because the lights automatically are magical, because it's a naturally ventilated building, but more to do with architectural form, that if you're going to make a building work that's going to be naturally ventilated, you have to build them basically on a shallower floor plate where people are in a closer proximity to either an external wall or a large atrium, the roof space, and therefore that more of the floor space can be lit using natural daylight for a greater portion of the time. So there are benefits overall. The one thing that does excite me is the light grey bar, which is office equipment. And this is to do with behaviours, in that if you actually create an environment which is sustainable, then in order for that to really work well, you would like to sort of have people like, in terms of procurement policy on where we go and buy things from, what sort of policies we put regarding the energy consumption of equipment. Do we all have lots of monitors, or do we get away with less energy? That sort of behaviours of what we're going to try and create with a sustainable office is alluded to by the difference between these two bars. So there's a lot that we can do. What are the barriers? Well, the barriers to moving towards, I'm going to say, a more naturally ventilated building, certainly a purely naturally ventilated building, are fears of, for example, thermal comfort and cold drafts and things like that in the winter, or indeed risks of overheating in the summer. And we therefore need to look at how we overcome those challenges if we're going to meet energy reduction targets by moving towards buildings that are going to be more naturally ventilated. But before we just think about thermal comfort criteria in the winter and the amelioration of cold drafts and things like that, what I wanted to do was just highlight what do we mean by thermal comfort. It's actually interesting that when you go and look at buildings that are mechanically ventilated and air conditioned, they're usually designed to be within a narrow temperature band, so plus or minus 2 degrees centigrade, for example, over the course of the year. This is a building that we surveyed some time ago in southwest London, 3 stories, generally open plan, and we're going to look at what happened to this building, even though it's got lots and lots of controlled equipment, so air chill beams, chilled ceiling, displacement ventilation, trench heaters, heat recovery systems. I mean, just had all the bells and whistles thrown at us. It was the engineer's playground, just absolutely wonderful in terms of the amount of equipment. Was it able to deliver plus or minus 2 degrees centigrade? So what you're going to look at here are temperatures, temperature on the horizontal axis, height from the floor to the ceiling, just on the first floor. That's the middle floor of a 3-story building, in 5 locations. I'm not going to show you any more data because it will get rather more complicated if I did that. Just look at this horizontal scale. I'm hoping that you will already smell a rat in that, because I'm an engineer, I'm trying to provide scales that are appropriate for a graph I'm going to show you. And we're going to look at what happens over the course of a 5-day period. It's a call centre 24/7 that was operated, and which is supposed to be designing this building and operating this building with plus or minus 2 degrees centigrade. And what you'll see is that this is far from plus or minus 2 degrees centigrade on a November sort of end of month period. It's really all over the place, and the variation between the floors was even greater. So this is important because what we mean by thermal comfort, we just need to make sure that we don't make a rod for our own back, that we set conditions that are deliverable and achievable. And if we're going to set such tight conditions of, say, plus or minus 2 degrees centigrade, it's going to be really difficult to do that with buildings that are not air conditioned. But even those that are air conditioned, we're going to struggle with this. So perhaps relaxing and just being clear about what we mean by temperature criteria will be a helpful way of overcoming one of those barriers to how we then go and move away from just purely mechanically ventilated air-conditioned buildings. So one of the other things that I wanted to indicate was that there has been a move because of this concern about buildings being drafty and cold, certainly in the schools arena in the United Kingdom, in naturally ventilated buildings now, drafts, what constitutes a cold draft has been defined and it's been excluded. It's been there for quite some time in mechanical ventilation systems, but not in naturally ventilated buildings. And that's been a positive, really positive attribute regarding trying to ensure that we're creating environments that are going to be comfortable. It doesn't mean that we can't do this, because there are systems designed we can deliver this criteria, but it means that we're overcoming the barriers to people's acceptability of buildings that are naturally ventilated. Before I talk about the strategies that we're going to suggest that are good for reducing the energy whilst also ameliorating cold drafts, I wanted to just share with you some experience of looking at a building in Manchester, the Contact Theatre, and it had some stacks on it. And these were natural ventilation stacks. The idea being that air would be brought in at the bottom into a stack and out through the top. This is what the theatre was designed to be. And conducting water bath experiments, which is where we're building the scale model of the airflow in the theatre using water flows in a laboratory tank by performing a laboratory experiment where you're trying to achieve dynamic similarity between the water flow in the experiment and the airflow in the building, teaches us something about the flow regimes. So I just want to show what's going on here. We have a 10 centimetre by 10 by 10 by almost 15 cuboid representing the interior of the theatre, two stacks, a hole at the bottom. There's a heating element in the bottom of this to represent the heat gains in the space. We immerse it in a large fish tank, shine light through it with tracing paper on the outside, and you're going to be able to see the density contrast between the cold water and the warm water to represent what will be the cool exterior air and the warm air in the theatre. So just watch what happens for these different experiments. The first one on the left, you will see that the stacks are outflow, but for exactly the same geometric conditions on a different day, we were able to show that you can actually achieve a different flow regime where the right-hand stack here is indeed inflow and the left stack is outflow. There's still inflow through the bottom. And then by perturbing that system, you can actually get it to flip. So that in this case, we've now got the stack flows have changed. This was a surprise, although on reflection, perhaps it shouldn't be a surprise because naturally ventilated buildings, there's nothing to say that you can't have inflow through a high-level opening. And when we go and look at older buildings, this has been happening for some time. The critical thing was the strategy that was being proposed was inflow through the bottom and outflow through the top. And in order to ameliorate cold drafts, even in the theatre, they had lots and lots of heating elements in the trench to go and make sure that the cold air coming in on a winter day was preheated by the theatre, even though the theatre had very high heat gains for the people and the lighting. Well, this taught us that, in fact, although this strategy was the one that was being designed to, the one that we wanted to actually use was where air would come in through the top and mix with enough of the hot interior air to ameliorate the cold draft. And thereby, instead of using heating elements to go and provide the draft mitigation, we're using the heat gains in the space. And this was a sort of a penny dropping moment when we looked at what the energy savings were. We were going to be able to at least halve the energy consumption of a naturally ventilated building by changing the strategy from inflow at the bottom and with preheating to inflow at the top and doing mixing. Now, this was absolutely phenomenal in terms of therefore realizing that we can create not only draft-free naturally ventilated buildings, but much, much lower ones. This idea was then explored further with some laboratory work, and then we went into the real world by getting this idea implemented in practice. So this was a prototype system that we built and installed in a primary school near Cambridge, and we then delivered thermal comfort to the children. I had at that time I had small children, primary school children, 5 to 7 years old, and they were sat. Some of them were sat underneath this particular device, just with their regular sweaters, on a cold winter day. The classroom was well ventilated. We had that checked with carbon dioxide monitors, but they were not freezing cold. And the heating was all being done by the people, the IT lights and solar, not by heating elements. So having demonstrated it, we then went and sort of took this to market and got some systems installed in a lot of schools. So this was the first commercial project that we did in Queen Alexandra College in Birmingham. And these roof stacks on the top, what you'll see here, for those of you who are into the design arena, you'll see that these roof stacks are actually not at the apex of the roof. They are not, therefore, being used to sort of just use the wind to go and drive the ventilation flow, especially in the winter. No, what's driving the ventilation flow in the winter is a buoyancy flow. The fact that half of the shafts are full of cold air coming in, it's called dense air, and the other half are warm shafts with hot air leaving. So we're able to ventilate the buildings, but we were doing some assisted mixing with very, very small amounts of fan power. These were ceiling fans just to disrupt what would have been a coherent plume of cold air dumping on somebody's head. We were then using that to disrupt the incoming air. And then the idea of these systems were then monitored and we showed that we were able to deliver the air quality targets that were mandated by the building regulations and Building Bulletin 101, which was the code in place at the time for schools, saying that the daily average carbon dioxide had to be less than 1,500 parts per million. This was delivered in all of the schools that we were monitoring, and it was a very, very satisfactory from an air quality point of view. But the most pleasing was that then we went and measured the energy consumption of these schools, and this is what we achieved. If you look at the green bars on the right-hand side, these are the heating bills for these two schools compared with, on the left-hand side, the typical practice and good practice. The Port Regis one on the very far right is actually particularly interesting. It was heated with a heat pump, and we weren't able to separate the heating bills from the lighting bills and the IT bills. So this is the total energy consumption of the building, and it's still way less than what would have been typical practice for heating alone in a building. So you start to get a sense of just what opportunities there are by getting the strategy right and then working with regulations that say we're going to remove cold draft. So the winter condition was really, really helpful. And this was launched in 2018, where this statement was in the revised guide to Building Bulletin 101. The design should, wherever possible, use the heat gains from occupancy and equipment and use this to warm the incoming ventilation air. Clearly, it meant you could still put the heating system in, but that system should only be used after you've availed yourself of the opportunity to use the heat gains from the others. So that was winter. Let's just talk briefly about summertime. And the big thing here that with some of the new guides is that they basically looked at what do we really mean by overheating. There are two factors. One is looking at beyond just air temperature, but operative temperature, because if you can cool the surfaces in an interior space, and if you're exposed to those, you can get radiative cooling. So that's the great thing with a lot of the design criteria now. In summertime overheating, TM52 with SIBSI, and ASHRAE have got similar guides. It's about trying to use the night cooling opportunities, creating interiors, which will then help absorb some of the heat. So we're all hot bodies, and we will radiate those. And that's a way of trying to avoid just relying on air conditioning. And then lastly, I just wanted to share with you that you can't always do it in a naturally ventilated, just pure natural ventilation. And therefore, I'm a massive fan, excuse the pun, of hybrid designs where you will do whatever you can with natural ventilation. It might mean that some parts of the building can be naturally ventilated, whilst others have to be mechanically ventilated. Or you have a building that's going to be part naturally ventilated for some of the year and part mechanically ventilated. So this is the Selfridges Mall, but it's the Bullring in Birmingham, and there the main thoroughfare is naturally ventilated. The retail units around the outside, which have got much deeper floor plans, are then mechanically ventilated. But it's a low energy overall scheme. This is a rather well-known scheme for hybrid. It's all on the internet. You can find details of that. It's the Apple headquarters in Cupertino. There's some lovely videos that Apple have put out. And this is a building where it's a hybrid in a different way. Every part of that building can be mechanically ventilated and air conditioned, but for about 70% of the year, it's in a very lovely climate. Basically, they open up the building and it's naturally ventilated. And one of the great benefits of this is not only has it got a lower energy footprint as a result of this design, it's a more stimulating environment for the employees as well, because you get lots of fresh air. You get, I would say, the nice vagaries of airflow moving through a window, the stimulation of the fact that you get wafting of air on a spring, summer day. It's a great working environment. And then closer to home, this is a further hybrid design. This is the Bloomberg building in London. That is also a naturally ventilated building for some of the time. It's such a deep floor plate, although it's naturally ventilated, there's some mechanical cooling all the time, because it was shown that we really needed to be able to avail ourselves of mechanical cooling just to take some peak lopping of some of the afternoons, even in the winter, for example, because of the heat gains in the space. So in summary, I just wanted to leave it with you that I think natural ventilation, is a low energy scheme, but in reality, I think a hybrid is often the best way of making sure that we really cope with occupant satisfaction. And I think one of the things that we will continue to see are, first of all, we've had changes in the regulations and guidelines to help us with improving the energy efficiency of buildings. And I don't think we're finished yet. I think there are going to be further improvements to promote hybrid, because the way that they're written right now is it's still looking at one scheme or the other. And I think we could do even more going forward to sort of see whether we can get the idea of hybrid as a way of really sort of into the psyche, into the building community. Anyway, that's what I wanted to share with you, Chris. And I'll be very happy to entertain any questions you might have.
Thanks so much, Shaun. Deeply fascinating and some really compelling data sets you've run us through there. There's been some questions in the chat. I think a very practical question from Don actually first is how long is needed to compensate the investment of installation from reduced heating bills, do you think?
So that's a really good question. Nearly all of the projects that I dealt with, the capital cost of the buildings was no higher than the capital cost of an alternative mechanically ventilated air conditioned building. So it wasn't a case of having to look for a payback period. The payback period was often zero. In other words, it was a cheaper building from the outset. If you look at the typical costs for mechanical ventilation, air conditioning systems and building services, you get to a decent chunk of the overall cost bar of a building, and it's many tenths of percent. A third of the building, maybe not quite half, but often a third of the capital cost can be associated with plant. So therefore, if we can therefore not have to install all of that equipment, we can often end up with a cheaper building.
Thank you. Another question is ventilation of buildings near the equator have issues with humidity to deal with as well. And from your research, are there any strategies to promote in these kind of areas?
So humidity is a very, very important factor. And if you are in an area where it is high humidity for a very, very large proportion of the time, then I'm afraid that actually mechanical ventilation, because of the dehumidification aspect to make the interior environment satisfactory, is probably where you need to go. However, there are also many parts of the world where it's humid, not humid for maybe 10 weeks a year. So I've done a number of buildings in North America which have this issue. And therefore, they are ideally suited to a hybrid where you have to have mechanical ventilation to do dehumidification, especially in the height of the summer. So if you go to, for example, the various like Chicago area and things like this, you have these 10 weeks in the peak of the summer. You also have some fairly cold winters as well. So actually what you'll end up doing is having a mechanical ventilation system that deals with, say, 8 to 10 weeks in the summer, maybe a similar period in the winter. And then for half the year, which are the shoulder seasons, you basically then run the building for free. Those kinds of buildings do typically cost more, Chris. So there is an uplift in the capital cost for those because you're doubling up. Not quite doubling up because you can often share the same pathways and ductwork and things like that. But nevertheless, they will cost more. But what you avail yourselves of is a lower energy building. I would argue certainly overall a more satisfactory building for the occupants because people like to be in contact with the external environment even when they're working when it's nice to be so. They end up with a more stimulating environment. You have increased occupant satisfaction, increased retention of staff and things like this. So getting a hybrid into our mentality is a really positive thing.
Thanks. And so speaking a bit more about the hybrid nature as well, and a question about the global south is what other strategies can we use in tandem to improve the ventilation situation? And the example here was incorporating vegetation and reflective roofs and ceramic tiles in addition to these things to alter temperatures.
So I would say that there's still more work to be done. As I said, I think there's more work to be done on guidelines and regulations regarding hybrid, but also just the greater use of natural products. And it's not just about, for example, what do we mean by having plants and things like that, perhaps or vegetation? Does that really affect the interior environment from an air quality point of view? Well, it might do, but I would say actually we need to look at some of the softer benefits as well. And this is where I'm an engineer and therefore would lean very heavily on the architectural community to help us teach what is it about actually the interior environment that we're trying to create. So working with, frankly, fascinatingly experienced and expert architects to try and create stimulating environments, interior environments. So therefore, I think there's a role for more natural things within the built environment, but looking perhaps at some of the softer benefits.
It leads perfectly into my final question before we let you leave. What would you have us as urban designers, as architects, as planners do tomorrow to make the biggest impact with your research?
Well, for urban design, so outside of the immediate building, I think there's a huge amount that we can do. So, for example, one building that I know a little bit about, which is the Bloomberg building. It's got natural ventilation as part of the strategy. It will really see the benefits of that. For example, when we see reductions in road traffic in London, where the air quality then improves, and therefore actually the idea of then having fresher air, cleaner air coming into the building. So just massively forward thinking. and thinking about what we really mean about streetscapes, the use of trees and things like this to help try and make cities cooler, for example, in the summer. I think there's a lot that we can do in terms of making the external environment more appealing and actually more satisfactory for more naturally ventilated buildings.
So it's pretty. I think we could almost certainly talk for hours, Shaun. And I'm gonna sort of end that there. And thank you very much, and let you get off to your next appointment. And we'll move on. Thank you very much.
Thank you very much indeed.